In previous chapters, we discussed the z-test and the t-test. In the z-test, we don't know the population mean, but we do know the population standard deviation. So we can find the z statistic and use table A to solve the problem. In the t-test, we don't know both the mean of the population and the standard deviation of the population. We are going to calculate the t statistic and use table D to solve the problem. Sometimes we want to compare treatment or conditions at the individual level. These situations produce two samples that are not independent. They are related to each other. The members of one sample are identical to or matched paired with the members of the other sample. We have several examples. The first one is pre-test and post-test studies. Look at the data collected on the same sample elements before and after some experiment is performed. So for example, if I want to know if this class has effect, so we can have a pre-test and we have a post-test. Then we compare to the result on the same sample element, which means our class. The next example, for twin studies, often try to sort out the influence of genetic factors by comparing a variable between a set of twins. For example, if we want to know if daily exercise can increase the height, then it's better we are going to do a twin studies. We have two sets of the member. Here, the two sets of twin samples serves as identical, or we said in this example is paired or matched. The next example is we can use people matched for sex, age, and education in social studies, allowing cancelling out the effect of these potential lurking variables. For example, if we want to study to find out if use wireless phones will cause cancer, then we can choose two random samples, and this subject means human being must better to have the same age group, be in the same age group, or possible same sex, and education that's not necessary. So we can sort out, cancelling out some other effect, the effect of age to the cancer. In these cases, we use the paired data to test the difference in the two population means. The variable studied becomes here x1 means the mean of the first sample, x2 means the mean of the second. Here is the population. So x1 is the mean of the first population. x2 is the mean of the second population. And we care about the difference. So we form and construct a new variable. It's called x difference equals x1 minus x2. And our hypotheses are h0 is there's no difference. So mu difference equal to 0. And HA, alternative hypothesis, is there is difference. The difference can be positive, so mu difference is greater than 0, or the difference can be negative, or we don't care positive or negative, we just care about if there's no difference. So mu difference less than 0 or not equal to 0. We can see from here, although we have two populations here, once we construct the new variable x difference, so there's no different from the test on one population. So what we discussed before is on one population, one sample. Here, although we discussed the paired or matched two populations, two samples, but once we construct this new variable, we can do the same thing. We can use the same procedure as the test on one population. Here we have one example. Does lack of caffeine increase depression? The problem is individuals diagnosed as caffeine dependent are deprived of caffeine-rich food and assigned to receive daily pills. Sometimes the pills contain caffeine and other times they contain a placebo. Depression was assessed. So here we have two sets of data for each subject. The subjects are numbered as from 1 to 11, so we have 11 subjects. And for depression with caffeine, and the measured data is, for example, for the subject 1 is 5. And the depression with placebo is 16. And for the second subject, with caffeine is 5, without caffeine is 23. And so on. We have all the data, the two sets of data for the 11 subjects. As we said, we want to care about the difference between the cases with caffeine and with the placebo. So we are interested only in the difference. So in this example, we construct our new variable. It's called the difference. So we use the placebo data minus caffeine data. So for the first subject, the 16 minus 5 equals 11. For the second subject is 23 minus 5 equals 18, and so on. The last one is 0 minus 1 equals negative 1. By this way, we transform the two sets of data point into only one difference. So now we can use the method we discussed before on this one population problem. For this one here, we know n equals 11. And so the degree of freedom equals n minus 1 equals 10. And we are given these 11 numbers. So we can calculate the mean of this sample, and we can calculate the standard deviation of this sample. So the mean is given by add all this together, divide by 11 equals 7.36. So the mean of the sample equals 7.36, and the standard deviation equals 6.992. So here we don't know the population standard deviation. So this is a t-test. The hypothesis we want to state is H0 is because we want to know if caffeine and the placebo has effect. So the H0 is the mu difference equal to 0. It's no difference. And the alternative HA, so this is supposed to be HA here, is the mu difference is greater than 0. That means there is positive effect. As we know, this is t-test, so we calculate the t value. The t is defined by x bar minus the mu 0, which equals 0 here. So this is this, x bar is this, and f is here, and n is 11. So n equals 11. And plugging into numbers, we calculate t equal to 3.53. Now we need to use table D because this is the t-test. In table D, and this here is again the degree of freedom, so we are looking for 10. So this is 10 here, so we are interested in this line. And in the center of the table D is the t value. So our t value is 3.53. So we are looking for somewhere, and we found that there is here is called 3.58. 3.58. And our value is less than this one. So our value is here. And so on the top, that gives us the p-value. So the p-value here corresponding to 3.58. That p-value is this one, 0.0025. And the next, the other side is 3. The other side is 3.169 corresponding to a p-value of 5%. This one corresponds to this percent. And our value will be in between this. So that means the p-value will be larger than 0.0025 but smaller than 0.005. So we can see this p-value. So p-value will be less than 5%, which is typically used for significant test. That means our conclusion will be our conclusion is we are going to reject H0. So this is our conclusion. So we can see from this example, the paired, the matched pair T procedures is almost the same as ordinary T procedures. We just form a difference between the two populations or the two samples. Then we just follow the same steps to do this. Okay, next we are going to discuss the robustness of the T procedure. The T procedures are exactly correct when the population is distributed exactly normally. If for normal distribution, the T-test is the same as the Z-test. So however, most real data are not exactly normal. But good news is the T procedures are robust to small deviations from normality. The result will not be affected too much. Factors that strongly matter, the first one is the random sampling. The sample must be a simple random sample from the population. So keep in mind, this is the first one. The second one is outliers and skewness. Both strongly influence the mean and therefore the T procedures. So outliers and skewness will affect the T procedures. However, if we increase the sample size, if the sample size getting larger, then those bad effects will be diminished. So if you do some like test, this kind of test, if your sample size is large enough, then the outliers and skewness will not be considered as a big effect to your result. Specifically, when n is less than 15, the size of the sample is less than 15, the data must be close to normal and without outliers. It's close to normal and without outliers. If your sample size is greater than 15 but less than 40, mild skewness is acceptable but not outliers. If your sample size is greater than 40, then no matter you have a skewness or you have outliers, your T statistic will be valid with even a strong skewness. In the caffeine example, the p-value calculated is less than 5%. So our conclusion is we are going to reject the H0. The fact behind the problem is HA is true and we reject H0. And this is good. In real life, this is not necessary like this. That being said, even HA is true, sometimes we are going to fail to reject H0. That means there is a probability, and that probability to reject H0 is not equal to 100%. That probability is called the power. The power of one sample t-test. It is defined by the probability that the test will reject the H0 successfully when the HA, this is H0 here, and this is HA, the mean is true. The calculation of the exact power of the t-test is complex, and it is beyond the scope of our class. So we do not discuss the details how to calculate the power of the t-test. Instead, I suggest you just read the textbook to learn some fundamentals of this. We have discussed the normal distribution. We are going to use the z-test. And we have discussed the non-normal distribution. It's called t-distribution. In that case, we prefer the sample size to be as large as possible. Right? The larger, the better. But what if the population is clearly non-normal and your sample is small? So that means we cannot use the t-test, z-test, and the t-test is not very accurate. How to do this? We have three methods to deal with this. The first one, if the data are skewed, we can use a transform method. We transform the variable to bring it closer to a normality. For example, we can use a logarithmic transformation. For example, the data are given x1, x2, x3, and so on. And we know that the distribution of that set of data is not normal. If we can use some transformation, for example, log, if we take the log of this log 1, x1, and log x2, and log x3, we get a new set of data. And this new set of data may be much closer to normal distribution or to t-distribution. So in that case, we take this new set of data and deal with z-test or t-test. So this is the first method. And again, we do not discuss the details of this method. The second method is we can use a lot of other models. It's called non-normal models, and to deal with this kind of problem. And again, we don't discuss details. And the last method is we can use a distribution-free. It's called Nonparametric inference procedure. That means that model applies to all distributions. So it's distribution-free. So this procedure does not assume any specific distribution for the population. Looks like this is too good to be true because this applies to any distribution. So definitely it will be less powerful than distribution-driven, for example, z-test or t-test. One example of this distribution-free model is the sign test for medians. And we are going to discuss in detail of this method, so sign test. A distribution-free test usually makes a statement of a hypothesis about the median rather than the mean. Right? So here is the difference. In previous unit, we discussed the population mean. We estimate the mean with z-test or use t-test. But in sign test, we are going to make statement of hypothesis about the median, not the mean. We are going to discuss the sign test for matched pairs. Assume we have a random variable x, and it is continuous, and we don't know the median m. It's unknown. The median m is unknown. Once we have this random sample x1, x2, all the way to xn, and we will be interested in testing whether the median m takes a particular value m0. For example, we said this set of data is given by 1, 5, 1, 3, 5, 7, 8, 10, 12. So 1, 2, 3, 4, 5, 6, 7. So suppose we are given these 7 numbers. We know how to calculate the mean, the median. So in this example, the median must be 7 here. But we want to test if the median takes a particular value, for example, m0 equals 6. I want to test if the median of this set of data is 6. We know from chapter 1 the real median is 7. But suppose this is large, I don't know that this is the population, right? So I don't know this. We only know the sample. So what I want to test is if the median of this set of data equals 6. So M0 here is 6. Our hypotheses are H0 is the median of the set of data is 6. So this is H0. And the HA is, again, we have a one-sided test on the left-hand side and the right-hand side, or we have a two-sided test. So right-hand side test is the median of the set is larger than 6. So actually from here, we know this is true. The median of set is 7, so this is 6. So this one here, this is HA, or it says the median of the set actually is less than 6. Or two-sided test is the median of the set is not equal to 6. So how to do this kind of problem? The steps is first one, we use the set of data X for each value of the set Xi. We subtract M0 in our example equals 6. So for this one we have for this one we get minus 6, so this one equals minus 5. And this one here is minus 3, and this one we get minus 1, and this one equals 1, this one equals 2, this one equals 4, and this one minus 6 equals 6. So first one, we subtract the M0 from each of the data. Then, because this is the sign test, we only care about the sign, not the absolute value. So for this, we said this is a negative sign, this is a negative sign, this is a negative sign, this is a positive sign, positive sign, positive sign, positive sign. And we are going to make our conclusion based on the number of positive signs and negative signs. So here is the summary of the steps, how to do a sign test for a median. Step 1, calculate the match, the difference for each individual in the sample. Second, ignore pairs with difference 0. In our example, our difference is not equal to 0. It's negative or positive. But if there is any difference equal to 0, we just ignore that. The number of trials n is the count of the remaining pairs, does not include the difference 0. Then we record n minus is the number of negative signs as we calculated here. So in this example, n, capital N negative equals 3. And then n capital N positive equals 4. So we write all these numbers. N minus and n plus. N minus is the number of negative signs. N plus is the number of positive signs. If H0 is true, that means M equals M0, then both N minus and N plus will follow a binomial distribution. Binomial distribution with parameters N and P equals half. Because N and P equals half. So we don't use Z statistic, we don't use T statistic. Instead, we are going to use a binomial distribution. So this is the difference than what we discussed before. The next one is calculate the p-value, then make our statement. P-value for one-sided test HA m greater than m0, we are going to reject h0 if n minus the number, in our example, n minus equals 3, is too small. So what does that mean, too small? Means the p-value for this one is less than or equal to n minus, in our example, which equals 3, if that p-value is too small. If this is true, n minus or p-value of n minus is too small, then we are going to reject h0. For the other side, the one-sided test, m is less than m0, we are going to reject h0 if n plus in our example equals 4, if n plus is too small. Alternatively, the p-value corresponding to this 4 is too small. For two-sided test, m not equal to m0, we are going to reject h0 if we care about the minimum of the two. So in here, one is 3, another one is 4, so this means this part equals 3. If this 3, the p-value for this 3 corresponding to 3, because this is two-sided test, so we have 2 here. If this p-value 2, p, and less than 3 is too small, then we are going to reject h0. Those procedures looks like tedious, but we are going to use the example to show how to do this. Actually, they are not that difficult. So here we have one example to show how to do the sign test. We have a random sample of 20 numbers. They are listed as 9.4, 13.4, 15.6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 20 numbers. We want to know, is there sufficient evidence to conclude that the median is smaller than 22? So that means our M0 is 22. If the median M0 equals 22, we want to test if the median of the set is less than 22. As we said, the first one, we need to state the hypothesis. H0, the M equals 22. And HA is, we want to test is the median is smaller than 22. So HA is M less than 22. Step 1 to do this is we calculate from this set of data by using this, each of this value subtract the M0, which equals 22. So this one minus 22, this one minus 22, all those numbers, the 20 numbers, subtract 22. And as we said, we don't care about the absolute value. This one minus 22 equals what? We don't care. We only care about if the result has a positive or negative sign. So we know that this one minus 22 will have a negative sign. This one has negative sign. And all the way up to this point, 21.9 minus 22, we get a negative sign. And this one, 23 plus 23.4 minus 22 gives us 1.4, which has a positive sign. So this one is positive, this is positive, 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 and positive. Okay, so now we know that N positive, which is the number of positive signs, equals 5. 1, 2, 3, 4, 5. We also know N negative equals 15, because here there's no difference exactly equals 0. If there's 1, for example here exactly equals 0, suppose this one equals 22, then this one equals 0, then N minus will be 14. And the N will be equals 19. We cannot count the number that with a 0 difference. But in this example, we do not have that 0 difference. So m plus equals 5, m minus equals 15. But for this test, for this HA, we don't need to care about this m minus. From here, we want to care about if this m is less than this one here. So you can see we only care about the m plus. We want to calculate the p-value related to the m plus. If this p-value is too small, then we are going to reject H0. Now for m file, m plus equals 5, we are going to calculate the p-value. The p-value is px less than or equal to 5. Keep in mind here is less than or equal to. For discrete variables, there is difference between less than or equal to. So we need to make sure there is an equal to sign here. From the binomial calculation we discussed before, the probability for x less than or equal to 5 equals the probability x equals 5 plus probability x equals 4, x equals 3, equals 2, equals 1, and equal to 0. And we can calculate this from the binomial calculation. And this, the sum of this probability equals 0.02, approximately equals 2%. And this one is less than 5%. So that means that this one is significant. So at 0.05 level, our conclusion is we are going to reject H0. What is H0? H0 is m is equal to 22. That means m is not equal to 22. We are going to accept this one. So m is less than 22. So here we finished the sign test. We can see the sign test is the difference between sign test and the t-test is the first one. When we calculate the p-value, we use binomial distribution instead of the table A and table D. Right? So we are going to use this. The second is once we test the median, we are test the median, not test the mean. So we are going to subtract the median. We want to test from each of the data set, each of the data. Then we only care about the sign. And based on here, if we want to test if the median is greater than some number, then we are going to test if the p-value is less than the n minus is too small. If we want to test the median is less than some number, then we are going to test if the p-value, which corresponding to the number of positive signs, is too small. If we want to do a two-sided test, then we are going to test the minimum for the n minus and the n plus.